Welcome to Periodicity in A-Level Chemistry. In this topic, we will explore how the properties of elements change across periods and downgroups in the periodic table. Course context and specification focus: development of the periodic table. Periodicity refers to repeating patterns and trends in the physical and chemical properties of elements when they are arranged by increasing atomic number. Periodicity provides essential foundations for later topics, including Group 2 chemistry, the halogens, transition metals, and thermodynamics. The periodic table arranges elements by increasing atomic number. Elements are placed into periods and groups based on their electron arrangements. The modern periodic table is the result of over a century of scientific development, and understanding this history helps explain why periodic trends exist. Early chemists attempted to classify elements based on observed properties. Dobereiner proposed triads, where groups of 3 elements showed similar chemical behavior and a pattern in atomic mass, but this model was limited. Newlands later suggested the law of octaves, noting that every 8th element had similar properties when arranged by atomic mass, though this broke down for heavier elements. The most significant breakthrough came from Dmitry Mendeleev, who arranged elements by increasing atomic mass but crucially left gaps for undiscovered elements and predicted their properties with remarkable accuracy. This demonstrated that chemical properties are periodic and linked to atomic structure. The modern periodic table is arranged by increasing atomic number rather than atomic mass, following the discovery of protons and the development of atomic theory. This change resolved anomalies such as iodine and tellurium. Periods, groups, and electron configuration. The structure of the periodic table is fundamental to understanding periodic trends. Periods are horizontal rows and correspond to the number of occupied electron shells in an atom. For example, all period 3 elements have 3 electron shells. Groups are vertical columns, and elements within the same group have the same number of electrons in their outer shell, which explains their similar chemical properties. For instance, all group 1 elements have 1 outer electron and form +1 ions. The periodic table is also divided into blocks: the S block, P block, D block, and F block, which reflect the subshell being filled with electrons. Variation of atomic radius across a period. Variation of atomic radius down a group. Atomic radius is defined as half the distance between the nuclei of 2 bonded atoms of the same element. Across period 3, atomic radius decreases from sodium to chlorine. This trend occurs because, although each successive element has an additional proton in the nucleus, the added electrons enter the same principal energy level. As a result, shielding remains relatively constant. The increasing nuclear charge exerts a stronger electrostatic attraction on the outer electrons, pulling them closer to the nucleus and reducing atomic size. Down a group in the periodic table, atomic radius increases. This is because each successive element has an additional occupied electron shell, increasing the distance between the nucleus and the outermost electrons. Although nuclear charge also increases down a group, the effect of increased shielding from inner shells outweighs the increased attraction. As a result, the outer electrons are held less tightly and are further from the nucleus. Definition and general trend across period 3, explaining anomalies in ionization energy. First, ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. Across period 3, first ionization energy generally increases from sodium to argon. This trend mirrors the decrease in atomic radius and is caused by increasing nuclear charge with relatively constant shielding. As atoms become smaller and the attraction between the nucleus and the outer electron increases, more energy is required to remove that electron. Although first ionization energy generally increases across period 3, there are notable anomalies between magnesium and aluminium and between phosphorus and sulfur. The drop from magnesium to aluminium occurs because the electron removed from aluminium is from a 3p subshell, which is higher in energy and more shielded than the 3s electron removed from magnesium. This makes it easier to remove despite the increased nuclear charge. The drop from phosphorus to sulfur is due to electron pairing in the 3p orbitals. In sulfur, one orbital contains a pair of electrons, and the repulsion between paired electrons makes it easier to remove one. Melting point and electrical conductivity, oxides and acid, base character, exam skills, data analysis, and summary. Across period 3, melting points show a distinctive pattern that reflects changes in structure and bonding. From sodium to aluminium, melting point increases due to stronger metallic bonding as nuclear charge and number of delocalized electrons increase. Silicon has the highest melting point because it has a giant covalent structure, requiring many strong covalent bonds to be broken. After silicon, melting points decrease sharply as elements such as phosphorus, sulfur, and chlorine exist as simple molecular substances with weak intermolecular forces. Argon has the lowest melting point as it is monatomic with very weak London forces. Electrical conductivity follows a related trend. Metals conduct electricity due to delocalized electrons, while silicon acts as a semiconductor. Nonmetals to the right of the period do not conduct. The nature of period 3 oxides changes from basic to acidic across the period, reflecting the transition from metallic to nonmetallic character. Sodium oxide and magnesium oxide are basic and react with water to form alkaline solutions. Aluminium oxide is amphoteric, reacting with both acids and bases, which reflects aluminium's intermediate character. Silicon dioxide is weakly acidic, while phosphorus, sulfur, and chlorine form acidic oxides that produce acidic solutions in water. This trend is closely linked to increasing electronegativity and decreasing metallic character across the period. Success in periodicity questions depends on strong exam technique as well as conceptual understanding, interpreting graphs of atomic radius, ionization energy, and melting point, identifying general trends and explaining anomalies. Using precise terminology such as nuclear charge, shielding, subshell, and electron repulsion is essential. In summary, periodicity explains how and why element properties change across periods and down groups. Understanding these trends helps predict chemical behavior. Thank you for watching.